All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying this time we have member ABC. ABC is rigid, so it's not going to bend or stretch. It's not going to deflect down at C when we put that force on there. But we also have cable BD. BD is made of 2014 T6 aluminum. Has a cross-sectional area of 0.5 inches squared. We want to figure the magnitude of the force P that's going to cause point B to go down 0.3 inches. So if we're tackling this problem, the very first thing we probably want to come in and do is say, well, I'm given a material here. Let's look in our book. Let's Google it. Look up somewhere material properties in here. We should get for this aluminum, RE, our Young's modulus, is E equals 10.6 times 10 to the third KSI. So I know that. I can also come in and say, well, my sigma y should be, again, pulling this out of a table. We can look this up a bunch of different places, but it's 60 KSI. These should be the same values no matter where we look, because it's a property of the material, not something unique that like a textbook author or that I'm coming up with in here. So we have both of those. If we're dealing with a problem like this, one of the things I found useful is to kind of lay out this graph, or not graph, this sequence. If I start at, that pen does not show up one bit in here. If I start at picking a different color, my deflection, my delta, I can get from there to my strain. So we'll say back and forth, because if I strain, I can get to delta as well. From strain, I can go back and forth to stress, because I know E in here. So to sigma, and sigma is P over A. So I can get to my force as well on this. For this problem, what do we want to do? Well, I'm given what's my total displacement, and I'm trying to figure out F. So we're going to start here. And then we're going to work towards F. Work towards our force F. It's kind of where we're going with this problem. So we know, let's just go through that. I need delta. I'll get from there to the strain, to the stress, to my force. So if I come down below and start trying to go for this, I'm given my displacement. So I know my very first thing I can say, 1, is my displacement of B. My delta B is 0.3 inches. Again, that's just from our problem statement. What's going to make it go down 0.3 inches? So from there, let's figure out what my new length is. So 2, let's get the new length. New length of member AB, of member BD, our cable of BD. When we do these problems, technically if this starts to elongate, member ABC is going to rotate as it goes down. B moves down and a little bit to the left. That movement side to side, as long as we are small strains, we're going to totally ignore, which for my class, we're pretty much always small strains. So we're going to say B only goes straight up and down. It makes our math way easier to work with because I don't have to tackle law of sines or cosines, which are the worst. Don't do law of sines and cosines. Just assume B only goes straight up and down. But so if I draw a picture of that, from A to D is no longer going to be 3 feet. We're kind of going to ignore where A actually is. We're going to add in my 0.3 inches. So making a new triangle that's 36.3 inches. Point A is really somewhere barely up above that. It's not going to play into this anymore. My width, though, and I got 36.3 because it's 3 feet, 36 inches, plus 0.3, 36.3. My width from A to B, well, if B only goes up and down, that doesn't change for us. So 4 feet would get me 48 inches. And I can get a new length here for that cable. Let's call that L2. That second length of the cable. And I can get that. My second length, L2, should just be, well, I can do the Pythagorean theorem. I have the x distance, the y distance, I get my new length. Also, let's notice, first off, we started out at 3 feet, 4 feet. This would be 5 feet or 60 inches. So how much are we changing in here? L2 is the square root of 36 let's do x squared, 48 squared, plus 36.3 squared, y squared. Or this is going to get me a new length of 60.1805 inches. So we're barely elongating, about 0.18 inches. If you're doing this, I would tell you work in inches, not feet. We're getting very, very tiny elongations. It'll get you the same strains coming out, but it'll be way easier if you deal with inches as you start to round anything off. But so we got that new length for everything in here. On my next step, we'll try to squish things together a little bit. Let's come in and say my step 3 is just going to be, if I have that new length, well, I have enough then. My strain is delta L over L, so I can get my delta L over L figured out right here. So what's my strain in this? My strain in the aluminum should be delta L over L. Or my change in length, well, that's my final length, 60.1805 minus my original 60 divided by my original length over 60. Or this is going to get me that my strain in the aluminum is 0.000300308. And I would tell you, carry a lot of sig figs as we come in and do this. But if I've gotten to my strain here, can I get to my stress for everything? Well, that'd be my next force in here. We're going to assume for step 4, we'll come off to the side here. I think we can get it in here. Let's assume that we are less than the yield stress. Assume sigma is less than or equal to sigma y. And we're going to check. And check. Basically, if we're not less than our yield stress, we can't do stress is force divided by area or E epsilon. We're out of our linear range on our stress strain diagram and things fall apart. So let's check and make sure we're in that range and our equations are valid. So our sigma aluminum should be E epsilon. And I have these values for us. My sigma aluminum is E. We looked that up. That was our very first thing we did. 10.6 times 10 to the third KSI times my strain. We just got it here, 0.00300308. Also, I should get units in here. We know it's technically a unitless thing, but realistically, my units for strain we report as distance per distance. This was inches per inch. So inches per inch would be my units on that. Those will cancel out themselves when we get here. My stress is still in the same as my E units, KSI. Or my stress here is my sigma AL should work out to be 31.88. 31.88 KSI. And if we compare that to our yield stress, we're about half of that. This is less than sigma y. Therefore, we are in the linear range. In linear range of our stress strain diagram. We haven't started to yield yet. Our basic equations are going to hold true for us. We should always want to come in and check that for everything as we plug through these. That has us to our stress. Can I get from stress to a force? Once I have the force, I could come in and try to apply equilibrium in here to figure out P. It's kind of where we're going with that. So my fifth step, 5. Let's find the force in member CD. And member BD, actually. And BD. So I have the stress in BD in our aluminum. Let's find the force in that. And I know my stress, sigma, is F over A. My force is what I'm trying to get here. I have my stress. My area we were given was 0.5 inches squared. So I can tackle this. Rearranging this equation, we get that the force, F, is sigma A. And I can just put in numbers in this then. My force should be my stress, 31.88, times the area we were given was 0.5 times 0.5. Or the force in this member, F, is 15.94. We have kips, if we write out our units, kips per square inch, kips per inch squared, times an inch squared. Those square inches cancel each other, and we should just be left with kips coming out for this equation. Which gets me to that F point. If I know the force in this cable, I should be able to find P in here. We just do that by applying equilibrium in here. So my sixth and final step in this is a free body diagram, because if I'm applying equilibrium, I better have a free body diagram that goes with it. So my FBD and solve for P and equilibrium to find P is our very last step. Kind of just systematically plugging through what were our steps that got us here. I'm starting at our delta, ending up at the force, and then using that force in a statics problem, realistically. So let's come in and do the statics piece of this. I have my beam. I know at the right edge coming straight down is my force P. I have in the middle of this 4 feet from either edge my B, and the left edge I have my pin at A. Even though I'm not going to use those, I should still show them. AY, and I have an AX in here. AX. And right here, I have my cable. That cable goes over 4 and up 3. This is a 3, 4, 5 triangle. But my force in here, I just found was 15.94. 15.94 kips. I have 3 unknowns in here. Realistically, I could find all of them. All I'm asked to do, though, is figure out my force P. And I can do that in just one equation. I have, if I sum moments at A, I'd eliminate AX and AY from this. I would have only P as an unknown remaining. Let's go there to get my final answer wrapped up. With positive, going counterclockwise, let's sum up our moments about point A. If I'm doing that, well, my 15.94, its X component passes straight through A. The line of action of A lies on the force's X component, so we'd eliminate that. The Y component will cause a counterclockwise rotation. So we'll add this in. I want the Y component, so the Y leg of that triangle, 3 divided by the hypotenuse, 5, times my force, 15.94. Force times distance gets us a moment, so times 4. P will cause a clockwise rotation, so I'm going to subtract that one out, and it's 8 feet away. So minus 8P is going to get us to 0, which I can solve that for P, and I'm going to get that the force here, P, is 4.78 kips, which is our final answer for our problem. Again, follow this process in here. To me, that's a really useful thing. I still write that out on my problems when I'm doing this, because it helps me think through where am I at, how do I move to that next step, and just really envision my game plan as I plug through everything. But But hopefully this was a useful video for us. If it was, stick around, watch more videos, hit our like and subscribe buttons. Let's get you an A with JJ.